All right, then let's start. Yeah, welcome everyone to the first workshop on progressive data analysis and visualization. I'm Alex Ulmer, and together with my co-chairs Jamin Zhou, Michael Sedelmeier, and Jean-Daniel Fekete, we organized this workshop because we think that PDAV is a very interesting research field and it gained a lot more attention over the past years. And it's very important in many domains where large data is used or complex algorithms. So we had a call for papers, which I want to talk first a little bit about. We called for papers with 2 to 4 pages of length. We had 4 submissions, from which 3 were accepted and 1 was rejected. Each of the papers received 2 reviews from our chairs. And we decided to have not them published to IEEE because it's the first workshop on PDAV, so we thought the short papers may not be already a thing that people want to be published, and it's easier for others then to reuse the contribution in future publications, for example, for larger conferences or journals. What we provide are the papers on our website. Also, each paper got the ability to provide a poster. There should also be a poster channel in Discord for these posters. Unfortunately, something went wrong with tech, and they're currently not there, but they are working on it. But yeah, for now, you can access the posters and papers on our website. Yeah, before we start with the program, here are the links to Slido on Discord, where you can ask questions. Also, feel free to already write your questions down during the talk because YouTube has a delay, and then we can immediately start with the questions after the presentation. Okay, and now on to the program. We decided to have multiple keynotes because PDAV has application in many domains. And our first keynote will be by Daniel Fischer about the current trends and technologies for PDAV. The second keynote by Julien Tiani will highlight PDAV in scientific visualization. And the third keynote by Barbara Hammer shows how PDAV can be used for AI and machine learning. Yeah, after a break, we will continue with the introduction of the upcoming book on PDAV by Jean-Daniel Fekete, followed by our 3 accepted papers. Yeah, the remaining time we will use for an open Q&A, and then we will conclude the workshop. So yeah, without further ado, let's start with the first keynote. While we switch the screen share, I will introduce our first speaker. Danielle, can you grab the screen? Yep.
Believe I got it.
Okay. So Daniel Fischer is a visualization researcher and independent consultant. He carried out research and user experiences around data visualization at Microsoft Research and built a data analytics tool for DevOps at Honeycomb.io. He's passionate about understanding how technology can support sophisticated user needs. The floor is yours.
Great, thank you so much. I was invited to give a keynote, I guess, because I wrote a paper a few years ago that helped get people excited about this PDAV space. And so I wanted to take a few moments to look at some of the factors around where we are for progressive visualization. That's partially because as I've had conversations with people, there's been a lot of like, yeah, but aren't we pretty happy with databases today? And I would like to argue that the time for progressive visualization is increasingly now. And yes, that's definitely meant to be a PDAV type joke. I realized that we haven't really unpacked the acronym PDAV, Progressive Data Analysis and Visualization. And I don't think I even bothered to put in a slide that tries to formally define it. In the book, we talk about it from a number of different perspectives, but one take is that it's visualizations that start with and analytics that start with a smaller sample of data and look at increasingly big samples of data, refining your result or a smaller set of computations, and then an increasingly big set of computations, refining your results until you have something more precise and crisp to show. This allows the user to have steerability on the way. They can choose to change some of the controls, and it allows them to interrupt things when they think they know the answer. If a 1% sample or a 0.1% sample of your data tells you enough, maybe that's a good time to stop. So why is PDAV exciting? Well, of course, one of the arguments is that it's good for big data. And so I've started off with what I'm calling the job security slides. It is not hard to find a Viz talk, or in fact, a talk somewhere in computer science that starts with the words, with the ever increasing amount of data, the world has stepped into an era of big data. This has been going on for a long time. Here's a 1999 CACM article that starts with, where megabyte data sets were once considered large, we now find data sets from in the 300 gigabyte range. Let's see, 1995, we've got people talking about the rapidly increasing amounts of information. So I think that it's safe to say that there is a rapidly increasing number of rapidly increasing articles about the rapidly increasing amount of data. I was certainly not innocent of this myself. This is a Hilda talk that I gave that also started with, we live in an era of ever-growing data sets. So I think it is safe to say that conversations about how big your data is are going to be followed with the answer, bigger than you currently expect and possibly bigger than that. So it's worth thinking about what techniques we want to apply. So I'm going to talk briefly today. First, I'm going to kick off with a couple of technical factors of some that argue for PDAV. I'm then going to talk a little bit about some things that I think are helping shape the market and are showing that the market is ready for PDAV solutions. And the rest of this workshop, I think, is going to be outlining some of the cool things about the technologies that are increasingly available. And Jean-Daniel will later be talking about the book where we try to coalesce the state of the art. Let's start with technical factors. I absolutely love this quote. Someone's talking about databases that can comprise a tape library of 200,000 magnetic tape reels, representing over 900 billion characters of data. That's 5,000 tape reels, 10 tons of tape mounted a day. Now, 900 billion characters is actually a small hard drive, today, but this is VLDB 1975. And so the challenge of what you do with big data has been distressing us for quite a while. This was a talk about the US Bureau of the Census, which had a real strong interest in being able to look at every single data point because US Census is supposed to count all the things and give as precise numbers as possible. That said, I think it's also useful to think about when you're dealing with 10 tons of tape, when you're talking about 200,000 magnetic tape reels, you have to think really hard about the sorts of algorithms and analyses that you're going to do. Looking at each tape reel is potentially very expensive. Looking at each tape reel twice is brutal, which means that questions that you need to ask need to be chosen such that you can do one-ish pass, through your data in fact, since we're seeing 5,000 tape rules over 200,000 magnetic per day and 200,000 total, that means that takes many, many days just to look at all the data. So that also helps us think about the idea that your storage time and your data transfer time might be important issues as you think about your algorithms. And in fact, researchers typically identify 3 different choke points: the amount of CPU, the amount of memory, and the latency to your big storage. Let's say it might be that you're limited by how fast your computer can run. You might be limited by how much memory you can store. And you might be limited by just how long it takes you to pull stuff down from the rest of the internet. And we are, in fact, running up against each of these choke points one at a time. A number of papers recently have started talking about the memory wall, the idea that bandwidth to memory and, in fact, size of memory is beginning to run into limits, that DRAM isn't getting much faster, and nor is it getting much bigger, and we're going to have to expect that we're going to see limited amounts of that people are going to start slowing down on the amount of memory that they can access. So you're going to have to choose what subset of data is going to be available in close memory. The same is sort of true of CPU. When I look at clusters, they almost are always sitting in the thousands of spaces, thousands of CPU spaces, and almost never much bigger than that. So, for example, if I look commercially today at AWS, their parallel computing service offers me virtually any scale. What does virtually any scale mean? It means that you can take a small scale of 32 nodes or a large scale up to 2,000 nodes. That's pretty great. It's really awesome that there's external services that let me get to 2,000 nodes. But that's also a fairly hard limit. And across a wide variety of different tools and places, we're seeing a pretty hard limit in the couple of thousand node spaces. And I think it goes without saying that remote storage is slow. There are lots and lots of sources digging around for the limitations of internet speed compared to as a tiny, tiny fraction of what your speed to local memory looks like. Now, with each of these choke points, you can make decisions. So, for example, if you've got lots of CPU but very little memory, then you can if a CPU is your choke point, let's say you've got very little of that, but you've got more memory, then you're going to, I think I labeled this backwards. If you got lots of CPU, then you're going to do lots of recomputing because it's not a big deal to run a number twice, and keeping a cache of that number is going to be expensive. On the other hand, if you've got lots of memory and very little CPU, then you're going to cache lots of stuff. We see other solutions, like if you're short on, if you've got lots of CPU, then you might run, but your network is limited, then you might be thinking about local first compute solutions, that is to say, running lots and lots of compute on your CPU. If your CPU is a limitation, you might try and cluster more. And if your network isn't too much of a problem, then you can try and parallelize and run things across multiple machines and have them talk to each other. So each of these is different solutions. But there's this one interesting thing of just do less. So if your network is a limitation, one good choice is to not look at it too much. Start with a sample of your data. If your CPU is a limitation, one choice is to do less computation. You could try sampling it. And in fact, if memory is a limitation, a sample can help you a lot there too. So the idea of looking at less data seems like a very strong one for an ability to scale. Let's turn over to the question of market readiness. I mean, one of the challenges that we've certainly run into has been that there aren't really progressive databases out there to build progressive visualization against. I think that that's unfortunately still true. But what's interesting is that we're in a world right now where we have agreed that the SQL consensus is kind of broken down. The world is not just relational tables, sitting on big iron anymore. The advent of things like columnar storage have made for people being more willing to look at databases that are optimized for either transaction processing or for analytic processing, depending on their goals and needs. We've seen trends like NoSQL and new architectures like Bigtable and BigQuery and Redshift. We're seeing commercial vendors producing memory local and network local databases. So if you've got data that is going to fit on a single-ish machine for some definition or another, you can have different databases that are optimized for those sorts of queries as opposed to ones that are built across networks. And more exotic tools like the blockchain and technologies like differential privacy have actually gotten people out there thinking about how you have to change SQL itself or change the fundamental architecture of the database. So there's opportunities for a market where, as we're building technologies, people will actually be able to put them to use and be able to ask these questions. There's an increasing market willingness to get the right database for your use case. The other constraint that we're beginning to loosen is that databases need to be precise. Um, I think a history of databases expected, like the census database, that queries should be exact. When you do a query, you're going to get a precise answer and you're going to get it, and you're willing to wait arbitrarily long to get that precise answer. We've been seeing a comfort with probabilistic data in more contexts, um, both because of things like probabilistic databases, because of entire fields like epidemiology that work off of statistical data. And a few months ago, I actually saw a couple of startups that are beginning to build out incremental query engines, things that give you partial answers. One of the interesting examples is a startup that I used to be associated with called Motif, um, which I did not drive this project. It was something that they ran into because they were running into compute and memory limitations and wanted to be able to get users answered faster. More so, there's been a huge change in the last year or two with working in an AI world where people seem to be a lot more comfortable with probabilistic answers and probabilistic and systems that are mostly right. And it's approximate. It's an ish future. And last, I think that we're beginning to see increasing demand for things that are going up in part because of AI systems that are going to have to give you partial results quickly because there's just so much compute and so much data to access. Um, so I've made up this scenario of like, you can imagine, say, a bunch of videos that you want to like pull some factoid out of. Show me a distribution of the game time and tradition of and position on the field that football players had an interception grouped by team. Unless your data is very richly pre-coded, you're going to have to go stare at an awful lot of videos. And while it's easy for an AI to make any one of these conclusions, when you change your answer slightly, instead of seeing the interception, show me the complete interceptions. Oh no, we have to rerun the whole query again. Again, incremental makes a huge difference there. We're going to see, I'm running short on time, so I'm going to conclude today by just saying, we're living in a world where technology is getting better for this sort of thing. And in fact, I think that the results of today's workshop are showing some really exciting possibilities in the PDAV space. And so I'm looking forward to seeing over the rest of this workshop what the future of PDAV will bring and what some of the opportunities are. And with that, I'm ready to take some questions.
Yeah, thank you very much, Danielle. We are currently not having any questions on Slido, but I would like to ask you one. You showed this interesting triangle with the choke points or bottlenecks for PDAV. Do you think that PDAV is kind of a remedy or a technology that fixes these bottlenecks also in the future because the data sizes are growing and of course the computation resources are always also growing, but there's always this race, and PDAV can kind of always be in the middle and mitigate the problems of this race. What do you think about it?
So that's one of the joys for me. As I was preparing this, I actually sat down with a couple of different colleagues and sort of said, what do you think is the biggest issue that PDAV is going to help us resolve? And one of them said, oh, well, clearly it's the memory wall. The memory is going to be a big thing and everybody's running into memory challenges. So thank goodness for PDAV because memory. And then I talked to someone else who's like, well, honestly, I'm more worried about like CPU and the amount of compute that I have to do. And the great thing about PDAV is that like I can run some number of iterations and feel like I've got enough. So when I started structuring this talk, I was thinking, well, let's go see which corner it actually speaks best to. And by the end, I sort of came up with I actually feel pretty good about all of them, which is, I hate to say it's a panacea. There's certainly limitations and things that PDAV cannot do, but it does, in fact, I think, speak to all of them. And so hopefully, as those limitations trade off in the future, the infrastructure that we're building around PDAV will simply be supported and improved.
Yeah, thank you. Yeah, one more question. What do you think the current technical infrastructure? What, of course, you had developed a couple of progressive systems, and how was your experience, and how do you think, on which level are we currently? What do we still need to do technically?
Ooh, honestly, I'd encourage you to like ask Jean-Daniel more about that question than me, who has done much more recently. Because I'll say that my own work was all built with a sense of optimism for the future and frustration with where we were today. That is to say, I was always building simulations of what PDAV could feel like, pre-aggregated data that we had aggregated across a number of different things so that we could allow users to ask multiple questions. Systems that automatically did too little data, but then slowed it down to show what it would be like if we had enough. Because you had to build out a full-on data infrastructure that was built in a different way. And again, Jean-Daniel and Michael and several others in this workshop have been trying to build out those infrastructures. But I don't think we're there yet.
Yeah, thank you. We have one question by Christian Tominski. What about the human as a choke point?
That is a great question. The best I can say there is that one, humans are always the choke point, and the purpose of having like an entire conference around that arguably is user experience around data, about making sense of data, this whole IEEE visualization, is because we're all worried about that. That is to say, it would be wonderful if we could just have numbers scroll past us like in the Matrix and just get our heads around stuff. But that's not how our brains work. And so we need to start understanding how our data works. And PDAV does have trade-offs, right? We've seen that if you do it wrong, you wind up with like weird little bouncy bars with like lines that are wiggling and shaking, and and users have to like make a decision of like whether the moment that they're seeing is done enough, or whether it's an artifact of something that might be more done. And we're going to see more challenges there. So I'm delighted that we're at a workshop where we get to sit down and talk about what the implications for users are.
Okay, we have another question by Hans-Jörg Schulz. I don't think we need to argue all the way up to the bottlenecks. Every unnecessary computation is a step away from sustainability. So PDAV is about making do with good enough analysis, not to brush the boundaries to even larger data or compute times, kind of killing the waiting time while waiting for the full result.
I could not agree more.
Yep.
That is an excellent point. And yeah.
Okay, thank you for your talk and for your answers, and thank you also to the questioners and now we will continue with our second keynote. Julien, you can grab the screen while I will introduce you. Julien Tiani, he's a research director at the French Research Center CNRS and is affiliated with Sorbonne University. He was awarded the IMT Young Researcher Award by the French Academy of Science. He is also the founder and lead maintainer of the Topology Toolkit, TTK, an open source library for topological data analysis. Please. Yeah.
Right. Well, thanks for the introduction, and hi everyone. It's a pleasure for me to present this work on progressivity in topological data analysis. This work was carried out with several colleagues, in particular Jules Vidal, who dedicated his PhD thesis to the topic, and the results that I will present today are coming from Jules' thesis. So this work deals with the analysis and visualization of scientific data. And in this context, data can come from acquisition campaigns, such as in these examples in bioimaging, or it can come from numerical simulations, like in these examples in quantum chemistry or climate modeling. And in both cases, a key challenge is the increasing levels of details that are available in these data sets. given the increasing resolution of the acquisition devices or the increasing power of the supercomputers that generate the simulations, pretty much like Daniel said in the previous talk. So these increased levels of details trigger the appearance of geometrical structures that are more and more complicated, such as these intricate filament structures in this confocal microscopy. And these intricate structures challenge the direct interpretation of the datasets, and tools are required to extract them, to process them, to measure them, and to compare them. And that is the purpose of topological data analysis, or TDA for short. So TDA is a set of techniques that aim at recovering the sort of intrinsic structure of a dataset. And to try to convey the philosophy of these tools, I'll use this map analogy. So what you see here is a satellite image of the scientific campus of Sorbonne University, right here. And you have the park next to it. And here you have the river that goes through Paris, and Notre Dame is somewhere over here. Well, this data representation is essentially a collection of very low-level measurements at the pixel level. And it doesn't carry any global structural information that is easy to interpret. So if we need to get from the campus to the other side of the park, this data representation may be somewhat useful. We can try to guess where to walk, but as humans, we usually prefer to interact with an abstraction of higher level, such as a map, where streets and paths are abstracted, and from which we can start to analyze structures such as paths between a point A and a point B. Well, the philosophy of TDA is to somehow extract an abstract map out of arbitrary datasets, such as in this example in quantum chemistry, where TDA tools have automatically extracted the atoms, the covalent bonds, as well as the non-covalent interactions between the molecules. So given a raw dataset, TDA will provide a reduced representation that describes the main structural features in the data, and which will be easier to manipulate for visualization and analysis purposes. So there's a zoo of tools that are available in the TDA toolbox. One of the most popular ones is the persistence diagram, which lists the features of interest as bars. Like here, for instance, you have 2 bars. And the lengths of these bars encode the saliency of the features in the data. And here you have those 2 large bars. This one encode the eye of the hurricane, and this one encode this region of high wind. There's other representations such as the merge tree, which encodes how features are related to each other in a tree structure. You have the Morse-Mat complex, which captures networks of filament structures. And you have the RIP graph, which is similar to the merge tree, but it can also capture loops in the data. And this work will focus on the persistence diagram. So the initial motivation for this work came from the VESTEC project, which was a European project dedicated to the problem of urgent computing, with applications in the management of crises such as wildfires, solar storms, or epidemics. And here the principle is that during a crisis, such as a wildfire, several numerical simulations are run to model the fire, and the produced data sets are analyzed on the fly to try to anticipate the future evolution of the fire. So from a computational point of view, this means that you want to provide some feedback to the crisis managers as fast as you can, such that they can take informed decisions quickly. And a relevant strategy for this is to consider progressive data analysis, where the system provides an approximation of the results that gets progressively refined if more computation time is available. So in the context of TDA, that meant revisiting existing tools to allow their progressive computation and their progressive analysis. And these 2 works were published in IEEE TVCG, but in the interest of time, I will only discuss the first one. Okay, so now we're going to get technical a little bit. So the input data will be given as a scalar field defined on a triangulation. And on this toy example, this is simply the height on this terrain. But in the applications, it can be pixel intensity values, electron density in chemistry, and so on. And the first information that we'll compute is the set of critical points of the data set. So for that, for each vertex of the triangulation, we'll look at its lower and upper lengths in dark and light green, which are the sets that contain the lower and upper neighbors of a vertex. And next, based on the number of connected components of these two sets, we can classify the vertex as being a regular point, a local maximum, like here, for instance, a local minimum, like down here, or a saddle point, like over here, in between those two hills. All right, so at this stage, we can list the critical points of a data set. However, for real-life data sets, you end up extracting a lot of critical points because the slightest oscillation in your data will create a critical point. So we need a way to identify the critical points which are the most prominent to distinguish them from noise. For that, we have something that's called the persistence diagram, which is obtained by sweeping the data from bottom to top and by tracking the lifetime of the topological features which are created or destroyed when passing a critical point. For instance, when passing the global minimum of the data, here at this point, we create in the sweep a connected component in the geometry. If we continue the sweep, we'll create a new connected component at another local minimum, and we can record that in the diagram as the birth of a new feature. And here, a third minimum triggers a new connected component. And if we continue, eventually components will merge on saddle points right here. And we say that a component dies upon a merge event, and its persistence is the difference in data values between the creation and the destruction. And that topological feature is represented in the diagram with this vertical bar. All right, so when we continue the sweep, we have a third component that merges into the first one, and we record the lifetime with this bar in that diagram. And we can now continue the sweep. And in that particular example, you have another minimum here, and eventually is going to merge with the rest over here, and you record this bar in the diagram. And finally, when the sweep is finished, the first component created in the global minimum is never destructed. It never merged with any older one, and we terminate its bar at the largest data value. Okay, so here I illustrate the process with connected components, but we can also track other topological features such as cycles, and these appear in this example on the dark green saddle points and disappear on the light green extrema. And we can record them as well in the diagram. So at the end, this diagram is a concise encoding of all the topological features that you have in your data with extra information about the birth and death in the sweep as well as the lifetime. All right. So now the question is, how can we compute the persistence diagram in a progressive way? And to answer that question, our strategy relies on a multi-resolution representation of the data. So we start with a low resolution, we compute the persistence diagram, and then progressively we increase the resolution of the data and we try to infer the impact on the diagram. And obviously here the target is not to recompute completely the diagram at each resolution change, but instead we'd like to deduce how the diagram changes based on the introduction of the new data points. So for that, we start with the original data set here, M2 on the right, which is the triangulation of a regular grid. And we consider downsampled versions of this grid, which we triangulate to obtain M1 and then M0. And then we will start the actual computation of the diagram in M0, move on to M1 and infer the changes, and then move on to M2 and infer the changes, etc. And eventually, we stop either when we reach the full resolution or on user demand. And here's an illustration of the same process, but in 3D. All right. So the key technical observation in this work is that as we jump from one resolution to the next, for a given vertex, the structure of its neighborhood does not change. So the consequence of that is that if the new neighbors, which are introduced at a new resolution, do not change their local classification into lower or upper, then it is guaranteed that the vertex in the center will not change its critical type. And we call such vertices topologically invariant. And in contrast, if we add a new vertex which flips locally from being upper to now being lower, we call this non-monotonic. And that means that for this neighborhood, we need to recompute the critical index of the central vertex. And there's a special case of a new vertex for which we can quickly identify if it is regular based on its neighbors. But the key message here is that for each vertex of the mesh, given the regular structure, we can very quickly decide if a vertex needs some recomputation or not. And the key idea is that we will only trigger recomputation where it is needed. So here is the overall algorithm. We first compute the critical points for the coarse resolution by looking at the lower and upper neighbors, and we compute the connected components of these sets. And next, we go to the next resolution. We first identify the non-monotonic vertices, and based on that, we can decide if a vertex is topologically invariant or not. And if it is, we just skip the computation for that vertex, we reuse the old result, and in practice, that represents 70% of the data. And for those vertices that are not invariant, we need to update their critical index by updating the connectivity of their lower and upper neighbors. And we initialize the new points. All right, so now we know how to compute critical points in a progressive way. And it turns out that for extreme imprecise diagrams, this part of the critical point extraction represents more than 85% of the computation. So what we ended up doing is that for each resolution level, once critical points have been updated in a progressive way, we apply the rest of the pipeline, the traditional post-processing, to obtain the persistence diagram for the current level. And here's a little demo of our progressive computation. So the data is on the left, diagram on the right, and here the user interrupts the computation at each resolution, and quickly the diagram captures the main features. And here, some hydrogen atoms are missing from the molecule, and going further into the hierarchy enables their detection and refinement, as you can see here. All right. So here are a few quantitative results. So an interesting aspect of this approach is that on average on our data sets, computing the critical points in a progressive way for the whole hierarchy was actually faster than computing the critical points from scratch on the finest level, about 2 times faster in our experiments. And a similar observation can be made for the persistence diagram. And here at the bottom left, you have a couple of examples where the progressive computation was faster, and at the bottom right, a few examples where it was slower. So to illustrate the relevance of our progressive computations, we have been using them in the VESTEC project to detect trends in sample simulations. And to do this, we used our progressive diagram computations, and we also used our progressive diagram clustering algorithms, which I didn't have time to present today. But overall, our integrated progressive pipeline enabled an ensemble clustering, which was very quickly correct with regard to the classification ground truth. And that enabled interactive feedback for the users. So this work still has a few technical limitations. Our overall framework assumes that you have a regular grid, and extending it to arbitrary meshes is an interesting challenge. Another aspect is that in our prototype, the progressivity is given by transitions between resolutions. However, the computation time increases with the resolutions. So the update frequency decreases with time, which can challenge the user experience. And finally, we guarantee the correct diagrams at the end, but the convergence rates could be improved. All right, so there's a few take-home messages from this work. So first, if you are not knowledgeable about urgent computing, now you can know that this is a nice playground for progressivity, because this is an application use case where there's a need to process the data as soon as it is available. Also, if you are not familiar with TDA, now you know that these tools enable a robust extraction of structural patterns, as well as their reliable analysis and with meaningful metrics. And for the work that I presented in particular, the key technical observation was that the local invariance of the mesh through the resolutions could be exploited to avoid recomputations as new data points were provided. We've shown an encouraging prototype for the VESTEC project with interesting improvement perspectives. And this work has been certified as replicable by the Replicability Stamp Initiative, and it is available in open source within TTK. And this concludes my talk. Thanks for your attention, and I'd be happy to take questions now.
Yeah, thank you very much, Julia. That was a very interesting talk. I was at first really surprised that it's possible to do it faster with progression than without progression, because usually we are always thinking, okay, if I compute something in one go, then it's faster than showing all the intermediate results. But yeah, it's very interesting how you describe it, that you use the intermediate results to have faster next intermediate results, and the speed up overall is helping so much that it's faster than just going to the finest level. Yeah.
So just to comment on that, I presented 2 examples where it was faster indeed, and 2 others where it was not. It's really data set dependent. And basically, if your data is very smooth, if you have fewer critical points, basically adding more points will just interpolate kind of a trend that you already have. And this multi-resolution scheme works very well if the new data points are just interpolating. That's kind of the intuition behind why, and in some cases, it's faster.
Yeah, and the other thing I wanted to ask is, you showed this short video with user interaction. So if the user zooms into a final level, then the computation is executed and progressively updated. Was this challenging to have these intermediate visualizations, the updates?
Yeah. The answer is absolutely. I guess Charles will discuss these aspects afterwards, but our library TTK is integrated in a larger visualization environment called PowerView. And the screen capture that you saw was taken from PowerView. And somehow we had to work around PowerView to make this happen. So basically, once our code is loaded into PowerView, it has right from the start a view on the complete data set, but it's just operating in a progressive way. And we can tune the progressivity by asking PowerView to ask at regular time intervals to ask our code for updates. So basically, we use kind of this time management feature of the software to have this sort of progressive loop. But it was a workaround somehow.
Okay, thank you. We have 2 more anonymous questions. The first one is, can you report on issues to integrate your progressive algorithm in a real tool?
Well, I have the impression that that question was a bit covered by my last comment.
Yeah.
If not, please feel free to clarify, and I'd be happy to answer.
Okay, the other question is, are the progressive clustering techniques published somewhere?
Yes. So basically, the clustering algorithm that we use is a very specific clustering algorithm. So basically, once we compute this persistence diagram out of a data set, what we do to cluster the data sets is not to run the clustering on the data sets themselves, but on the persistence diagram. So we have an algorithm that computes averages on the metric space of the persistence diagram. And once you have that algorithm, it's very easy to take it and to move it into k-mins. Because in k-mins, one of the core geometrical features that at some point you want to compute some barycenters. And this is how it works. So in short, yes, this is published somewhere. This is the second paper that I referenced at the beginning and that I didn't have time to talk about, but this was presented at Viz 2019 in Vancouver.
Okay, then thank you again, Julia. and thank you for the questions to the audience. And
Thank you
we
very
move
much.
on to the third keynote. Barbara, you can take over the screen. And yeah, I will introduce you. Barbara Hemmer chairs the Machine Learning Research Group at the Research Institute for Cognitive Interaction Technology at Bielefeld University in Germany. She is an active member in multiple national and international committees, such as the IEEE CIS for data mining and neural networks. Her areas of specialization include trustworthy AI, lifelong machine learning, and the combination of symbolic and sub-symbolic representations.
Thank you very much. So you see the correct screen, that's correct?
We are currently seeing your presenter.
Yeah, then this one is okay?
Yeah, that's good. Yeah.
Excellent. So thank you very much. So actually, I would like to talk about the pendant of progressive analysis in machine learning, which is probably incremental machine learning, which is actually the opposite of what one usually considers. So the classical scenario in machine learning is that you have a batch scenario, meaning that you have a number of data points given, and these come from a probability distribution. You see that on the left side here, that you have, wait a moment, I have to search for my, you see on the left side that there is that you infer from the given data points a model, and then on the right side, you would, after delivery, test or use your model for new data to come. And usually in machine learning, you are interested in the generalization ability. So you evaluate how in some loss function your model behaves on new data, meaning you compare h of x, which is for new data, compared to what you would expect, which is y. Now, in incremental machine learning, you go away from the batch data given, but you have a stream of data. So you have at the first point just one data point, another, and you would like to have a machine learning model at every point in time after having seen just data up to a number of time steps t. And usually you do it by being allowed to adapt a model. So if you have ht, you get new data point xt, yt, then you adapt your ht based on what you would have expected based on the xt. The cool thing is, in such a setting, you can also entangle learning and testing whether this is correct or not, because you can, while learning, already test, which is called the interleaved train test error, meaning that if you're at point t-1, you have your model ht-1, you can observe what it would lead as an output for xt before adapting it to give yt, meaning you have the loss function of ht-1 of xt given yt. And this way, actually, you can be even better with an online learned model than a batch one if the model you need at a particular point in time is a different one. So besides dealing with huge data sets, this is also super relevant for model individualization. And I have shown here one example, which is where we more or less started with this topic, which is a collaboration with the Honor Research Institute. So here the idea is to support people when they are moving. The final goal would be to optimize exoskeleton control. And for controlling exoskeletons, you need to know very early on what a person is going to do. So what you do is you put initial sensors on a body with, for example, in this case, an XN suit. Then you observe the measurements put on the body, and you try to classify what the person is going to do, whether the person is, for example, squatting up with an object where you would initiate support. And here you can ask yourself, is it better to deliver such a classification task if it has been trained on many people? Or is it good after delivery to observe a single person and adapt to a single person while observing what the person is doing and how the person is behaving? And actually what is the case is, which you can see on the left graph, that if you learn such a model on many people, then you will get a pretty good model pretty quickly, but it doesn't get as good as if you would adapt an individual model for an individual person, which would be the personalized one. And this is a fact which occurs also independent of different ways to represent the data. So we tried when we just represent the data with a single frame or more frames, or if we do some pre-processing. Meaning that this progressive learning, so to speak, or incremental learning is a very cool thing to adapt whatever you want to get the models towards the personalized needs. If you want to do so this is more or less a solved problem, how to do incremental learning. So there's this very beautiful river toolbox with many algorithms around, which is from Albert Biffet Groups. So there are many overviews since years, so since 2015 up to 2022, 23, 24. And if you want to play around with incremental data sets, so for example, this initial measurement data set from people, there are some publicly available. You see that on the lower left. I would like to talk about one specific phenomenon, which is making this hard for machine learning and probably also for visualization, which is the presence of possible drift if the data occurs. So imagine you observe data over time because you refine the data or it's just arriving over time. Then it might happen that you have what is called drift, meaning at one time point as compared to a later time point, the distribution of the data is a different one. So you have 2 points in time, T0 and T1, where the underlying distribution is a different one. And this is a problem for models because it might happen that the model you have built up so far is inconsistent with later models. And this might just be due to the fact because the data are not achievable via independent sampling, but you have it stored at different places in a distributed fashion. It might be that it's arriving over time. It's from one lab, from the other lab. So it might be that there's a problem here. What one usually now distinguishes is if you look at drift, whether the drift concerns the data only. For machine learning, often you have not only the data, but also a goal. So you want to learn, for example, classification, whether the data lie at different places in the input space, or you also have a different model derived thereof as concerns the labeling, which would be real drift versus virtual drift, which would concern the input data only. In addition, you might have different time frames in which the drift occurs. So it might be rapid, incremental, gradual, reoccurring. So you might have many different problems here. And I've brought one very simple example where you actually can see drift in natural data. So this is an image where you can just have a mock-up task of classifying regions of the image according to what do you see here. So is it the Palazzo Pitti or Palazzo whatever? So you want to classify the local regions. And you see that there's one Palazzo marked where on the right upper part you see the average color histogram taken over the whole thing. And you see the color histogram is changing dramatically so that over time, if you consider this in the morning or in the afternoon, you have completely different data. And actually, this is one mock-up training data set. So we call it Rialto Bridge, where you can play around with methods and see whether they can deal with drift or not. So when we have drift, there are actually different challenges you have to deal with. On the one hand, you might want to learn with drift, and all the incremental models can do that. You might want to detect that drift is happening, meaning you have to substitute one model you inferred by another one, which would be drift detection. That's a question, when does drift occur? It might be that you deal with what would be called drift localization. This is a question, where in the data space is a drift? Or you might ask the question, why? What makes a drift? And that would be explainable AI for drifting scenarios. So what makes up the drift and what is happening there? And I would like to look into the latter one, which is like a very emerging area in AI. So explain what has changed and why. And I want to introduce one, say, progressive XAI technology, which is incremental feature importance, as an example for a bunch of different possibilities. I would like to introduce this one because it's so intuitive. So how to compute feature importance incrementally for a possibly changing model. Let me introduce what means feature importance. That's a very basic and very common, very useful expandability technology. So feature importance values means you have some input data, whereby the input data is characterized by features. So you have not only an X, but feature 1 to N. And you have a model. Probably you also have a region of the data space where you're interested in. Then a feature relevance or feature importance measure would assign to each and every feature an importance value from the real numbers, telling me first feature or second feature or third feature has this or that importance. Let me show a very illustrative example. So in machine learning, it's sometimes hard to get accepted to conferences. I'm not sure about information visualization, but it might be the same. At some point, as a machine learning person, you might think about, okay, I just accumulate all my papers and I look which papers get accepted and why. And I can do so probably by using tabular data. So I represent, is my paper about deep learning, yes or no? Does it contain a proof, yes or no? Is it well written? And then I see, oh, the first paper was rejected, the second was accepted, the third was rejected, and so on. Feature importance values would now tell me with some number, okay, it's important to have it well written. Deep learning, probably medium important. Written by ChatGPT is not important at all. But of course, loving chocolate is very important because that's a hidden cost to have papers well written. If you want to get such bars, so these relevance bars, then one very popular and old technology is what is called the permutation feature importance, where the idea is, if you, for example, want to see whether the paper being well written is important, you permute the entries only in this feature, like that. And then you check where the output changes. And you then consider how much does the loss function change if you permute the feature. And that gives you the feature permutation index, which is given by this formula. So you have, if you look at the relevance of feature I, you permute the feature number I through your data set and you look what is the impact of this permutation concerning to the original model. But this is batch. We want this progressively. You see this as a sketch on the right part. So you have a data stream or increasing number of data. For machine learning models, you would also have an adapted model, which is it's a decision tree in this case, where you see on the very left part, a very small decision tree, it gets bigger. At some point, it's no longer the feature A, but the feature B, which gets important. If you have a very good machine learning model, you would not see any drop in performance, but the model is a different one. So you have drift in the data and one feature gets important rather than another one. So you would like to see that in the beginning of your data stream feature, the pink one is relevant, whereas in the later scheme, your violet one is relevant. Meaning you would like to have for each and every point in time, such a feature relevance or feature importance, telling you how important is which feature at the moment for your considered model. And that does need not be a machine learning model, but it could be anything which is differentiable, where you can play around with features. So it could, in theory, be also a clustering model. It could be a geometric model. Anything where you have a quality can be put here as a model, and everything which you can identify where you can permute could be a feature. So it's not restricted to machine learning classification models. Now the problem is, if we say we want to compute this permutation feature importance for incremental versions, then it's this scenario like that. So for machine learning, you have first one conference, which might be IEEE VIS. Then you have the NeurIPS, then you have ICML. And you don't know the output of ICML when you have to compute the feature importance for IEEE VIS. So you cannot permute this, this feature through everything because you don't know yet how it will look like in the future. Therefore, what we did is we looked into the model itself, and we found a surrogate, because what you can see is that this permutation is just a mathematical way to instantiate sampling of the marginal distribution of a feature. And you can also prove that, which is a lower equation. And this gives some insight or inspiration for a alternative incremental feature importance method, because what you now can do is you can just, instead of permuting for each and every point in time, sample from the marginal distribution and update the marginal distribution. And we did that with what we call reservoir sampling. So if you say you have no drift, you could just store all data points or histograms out of that. If you might have drift, you can store just what we would call a geometric sample, meaning we just store L points and substitute in a new setting one of the others randomly, which gives us a geometric distribution. And then we use this to update where the drop or change in performance with the sampled versus the observed feature, the feature importance. That works. So we had situations where we knew what are relevant features, and we changed, on the one hand, the features or the function, and we could observe that this is actually following the true distribution. And we could also show that the geometric sampling is somehow much faster and more reliable than non-geometric sampling if you have drift. And you can also do math in the sense that if you would have no drift, that this method converges to what you expect, limiting the variance. That is just one example for explainability methods for incremental ones. So permutation feature importance has drawbacks. They are much better mathematical methods, such as Shapley values, and we did similar things there. I'm not going to show those due to the time constraints. But I would like to have one very short glimpse at a more general setup. So this was one example for explanation in changing scenarios. One can go much further by having this idea, okay, you have a model and you would like to have explanations of changes or drift or incremental stuff. And the underlying scenario, which opens like an infinite number of possibilities, is the following. Whenever you have observed data, you can have a model out of it, which is either a classification model. You could also put models there which deal with the time and drift domain, such as what you see on the upper part, distinguishing whether you are before or after a drift, or you can also do what I would call drift segmentation, so decomposing your space into parts which are drifting in the same way. And then you can apply to such a model explainability technologies, and in machine learning there are many, allowing you to have different insights into what is happening with your data. I have one, and that's my very final example, where we did drift segmentation. I will probably go over this one and just show the result. So we use such a method to actually identify sensor faults in water distribution systems, where we just observe pressure values, and we wanted to observe which pressure values are faulty, where the problem is that everything changes because of changing demands. And what we did is we decomposed the drift into homogeneous ones, and then we explained, using the incremental permutation feature importance, what exactly caused one drift to look different than the other, which led us to, which you see on the lower part, to identification of sensor faults in such networks, although everything changes because the drift was behaving differently. So let me conclude. So incremental learning is the analogon to progressive analysis for machine learning. And there you have this drift phenomenon, which is very important. If you are not able to really watch your data, then that's a very common phenomenon. You can also do here incremental explanation technologies, and with model-based approaches, you have a huge variety of methods at your disposal. And I had a huge variety of money givers at my disposal, whom I should thank, and also all my colleagues on this last slide. Thank you.
Yeah, thank you very much, Barbara, for the talk. It's very interesting to see how progressiveness is included in AI and explainable AI. Yeah, I for myself have also the same problem. We training a model with a huge data set, and then yeah, we want the user to upload his own data and extend the model, and it's yeah very difficult to deal with this totally different data that's getting to the data set. And my question would be, I'm not really sure how to handle it best, adding data to the model. So should I add each data entry by itself, or just gather batches and add to the model? It's like I'm not sure what would be the best way.
Yes, I think this is a question which is super relevant. One thing is, it's not clear whether one would assume that each and every data points would accumulate, and whether they are controversial. So it might be that some person is adding data on the one hand, like trying for poisoning or stuff like that. So I think one would first time need to guarantee quality. And there, of course, yeah, some boxes, some things. So for example, what you could do is you could, with drift decomposition, see whether the data are somehow aligned with what you see. Then there are, I think there's a question now, I would always add in batches. So this incremental version is like an extreme, where you say you change after each and every data point. But in practice, one would always, I think, add in mini batches, depending on the demand. And one problem is, even if it's in line with the model you have, it might be that you have systematic changes. So if you, for example, have medical data, often people have a little bit of a shift or drift. And there, what one can do is one can do alignments that, for example, what we did is that we have the topology matching, such that you have a transformation which gets rid of a systematic drift. That would be one thing, but I think it depends very much on the application which you have.
Yeah, thank you. That's already a very good recommendation. And I think, according to this, also a fitting question by Jean-Daniel Fouquet, drift can be temporary. If you learn about Venice buildings over a day, you will see drift. But if you continue in weeks, the drift will disappear.
Yes, that's completely true. So there's also the question, of course, for deep learning, one hopes that one gets invariant representations, which abstract from small changes which you don't want to take into account. The problem is, of course, with vision, that people have the Gestalt laws. Deep learning or machine learning doesn't. So it's always an approximation. And actually, we tried with deep learning models. These are also affected if you have also, yeah, some illumination changes. So these are also affected if you go for extreme settings. So it's not solved, I would say. I would like to have an advertisement. So the SAM-KNN, the model we developed, that's capable of preserving things it already saw, which is still relevant. So there are incremental models which can deal with it. But
yeah, sure. It would be great if you can link it also on Discord, so
yes,
people can
I'm
find
happy
it.
to do that.
Yeah. Yeah, thank you again, Barbara.
Thank you.
I
Thank
don't
you.
see any more questions. It was a very interesting talk. And also thank you to the audience. We are now going into a short break and we'll be back in 15 minutes, if I see it correctly. No, in half an hour. In half an hour, we will be back with the second session.
One small question, can you throw me out? Because I cannot move the mouse to the other screen. That would be fantastic.
Yeah.
No, I have it. So no, I find it. Thank you.
Okay. See you in a half an hour. Bye.
So I think it's time to resume. So welcome back, everyone. I hope you had a chance to refresh during the break or grab some coffee. It's near midnight in your time zone, like me. And let's resume the workshop. And in the second session, we're going to have 4 interesting talks. And as a quick reminder, if you have any questions, please feel free to use the Slido app or the Discord channel. We'll be addressing questions after each presentation. For the first talk, I'm excited to introduce Jean-Daniel Fickett, who is not only the chair of today's workshop, but also the main editor of the book, Progressive Data Analysis, Roadmap and Research Agenda. This book was co-authored with several authors from the Progressive Data Visualization community, and Jean-Daniel will share valuable insights on the book and the field. So please welcome Jean-Daniel.
Thanks a lot, Jamin. Can you see my screen?
Yes.
Good. So, okay, let's do it. So now I'm very happy to be able to present quickly this book at this workshop. So this book has been prepared for many years and will be available soon. It's in the last step of its preparation. So the book started a few years ago. It's one of the last book that has been entirely written by humans. So I just put a stamp on it so you remember. The next one are going to be helped a lot by ChatGPT and his friends. And you see the new nice cover of the book. It's a nice mix with some images from Jamin's work and some nice blue sky. It's been edited by myself, Daniel Fischer, and Michael Sedelmeier, and it's the result of workshop that a seminar that we did at Dagstuhl, and all of the authors, most of the authors are from this Dagstuhl seminar in 2018. So if you remember, after 2018, there's been the COVID for a few years, and then now we have been able to wrap up and to bring people together to finish the book. Notice also that the participants of the book are mostly from the visualization community, but maybe are also from the database community and others from the machine learning community, or in between the machine learning and visualization community. So this is an important point to keep in mind that it's harder and harder to do research in silos like we used to do before. So as visualization researcher, I think it doesn't make much sense to only work in our field and not talk to other researchers. But for this particular domain, progressive data analysis, it's completely required to be collaborating with colleagues from other domains, because it's a very hard a problem. So the book addresses the problem, and it's not a book that says here is what has been done in the past. It's not a survey book. Also, it contains a survey, but it's mostly a book, a roadmap that explains what's left to do. And this is because progressive data analysis is at its infancy. What I like to do is to take the system that has been described by Brian Gaines in '91 for describing advances in technologies. It's called the Bretham model, and I like it, where Brian Gaines explained that all of the technological domains are advancing through multiple stages. At the beginning, you have the breakthrough, then it goes through replication, then empiricism, theory, automation, and in the end, maturity, meaning that everybody agrees it's important and it's used every day. And some technologies can fail because they are stuck at some points in their evolution. And right now, we had the breakthrough maybe 10 years ago on progressive data analysis, but still we are stuck in the replication phase. And the replication is difficult, is hard, much harder than what we had before, I think, in visualization. We had multiple stages to create the visualization reference model and then different aspects that led to the grammar of graphics, etc. So those were milestones in the evolution of visualization. But now with progressive data analysis, we need to merge the domain of data management and large data management, data analysis, including machine learning and other computations, with visualization and interaction. And so at this point of time, most of the things we see on progressive data analysis are still prototypes or early or usable prototype, but still prototypes. We are still replicating the initial idea, trying to find out how to do it well, how to do it more simply. And we haven't reached yet the next stages. And we need to accelerate this thing in order to make progressive data analysis a reality for researchers, but also for practitioners as well. So this is the current situation. And so this book is meant to accelerate the steps going through replication faster and then going through the other ladder of the model in order to make it available for everyone. So the book is organized in this structure: data management, data structures, machine learning, visualization, the human in the progressive loop. Uncertainty is also of interest to all of these stages, and how to evaluate system is also cross stages, and the book talks about all of these things one after the other, explaining what has been done and what should be done. And in addition to that, there is an introductory chapter and a chapter about concept and definition that contains interesting and important things for helping develop progressive data analysis. So let me talk about some of the highlights of the book in order for you to understand the challenges and also the potentials that are really huge. So just to be clear, progressive data analysis is really scalable and it works. All the prototypes that have been used show that you can scale to many orders of magnitudes higher than traditional visualization because PDA handles latency very well. And for example, we developed these medical visualization systems. In the past, systems such as this one visualizing medical events for people having treatments were limited to 50,000 to 100,000 events. Now we go to billions of people with thousands of events with a progressive system, and it works very well, and the system is quite easy in terms of implementation, and the interaction is very smooth. So the first thing to say is that it's not a dream. Progressive data analysis works, and the applications that are using it are able to scale to much larger scales than before. So what we want is now to be able to develop that for all of the possible applications so that we can use them on large data sets or complex algorithms. And so this book explains how to do it, but the first thing that it explains is that this notion of progressive data analysis is ambiguous to many or unclear to many. And many researchers or practitioners are mixing it with concepts that they are more familiar with. So every time you talk with somebody about progressive data analysis, you have a high chance of stumbling on somebody who will say, oh, it's exactly like online, or it's exactly the same as iterative, or it's the same as incremental streaming, or choose your other concepts. So these things might seem not super important, but it is very important because this is part of the confusion that we all see when we try to develop progressive applications. And I think it's very important to remember that when trying to have funding on a progressive system or to describe a progressive system as a paper, to make sure that we are not misunderstood. So the chapter number 2 clarifies the differences between all of these concepts in order to help explain them and avoid being trapped into this strange problem of having to explain why it's different from X, whatever X is in this long list. So that was a surprise to us, but we help you explaining that. One other very important highlight we have is that the progressive data analysis needs a programming paradigm, but behind it, because it's not like a regular programming. It's not like you call a function, you wait, and then you get the reply. You need to do it, but you need to maintain the latency. And in order to do that, you need to do it differently than the traditional function call. And so everybody in the database or machine learning or visualization field are all dreaming that they will take an existing set of library and just make them progressive with a magic wand, but it just doesn't work like that. There needs to be some adjustments and some changes in the way we program libraries in order for them to become usable in a progressive environment. So I think we need to adjust to this and to accept it. And the sad news is that there is not yet any infrastructure or language to do it. But the good news is if you're a researcher, it's a great opportunity for you to try and provide some examples in order to advance in this direction. So I think this is something that we should all be aware. If we need to go to progressive, we will need to rebuild something like a language or a set of mechanisms over a language so that progressive can work. And I don't mean by that this is very difficult. Technically, adapting algorithms is not always difficult, but it requires reaching down to lower levels of the libraries. And so this is something that is not very familiar to many. So that's really something important to keep in mind. But that's also exciting because we can recreate some new languages and new tools to solve new levels of problems. The good thing is that many algorithms have been adapted to progressive data analysis. And so the landscape of available algorithms is not small. And Julien has shown how to adapt some of the algorithms for topological data analysis. There's been many of them. So this part is possible, but they need to rely on some particular data structure that should be progressive. And again, they are missing from the standard toolbox and they need to be available soon. Same thing for visualizations. There are many visualizations that are available progressively, There are a few issues to solve, like stability, that are sometimes difficult, but this has been done. So let's continue this evolution, and that's great. One of the very challenging part is the uncertainty, managing uncertainty. We need to have an assessment of the quality of the result to know when we can stop sampling and have a decent result. And I was dreaming that we could connect multiple modules that doing computation and visualization, and then have a way to compute the uncertainty or the quality by combining the pipeline stages, but that's not working like that. So we need more time to find generic ways of computing uncertainty over a progressive pipeline, and that's really research, and that's great. This is a new set of problem, how to maintain this progressive uncertainty over large computation pipelines and show it with visualization. So that's really a research work. So just to summarize, we have a lot of exciting scientific and technical challenges. I think they are very important. Why would we do that? Because currently there is no other paradigm that can offer scalability for managing big data. And we are already lagging behind all of the other domains like databases, machine learning, or simulation. So we need to catch up with them. But I think the caveat is that we need to work with our colleagues from this other domain, databases, AI, ML, and simulation, because we cannot do it all by ourselves. In the visualization community, we've been trying to rebuild our own databases, our own ML systems. At this stage, for scalability, we cannot do that anymore. We need to work with people who are extremely skilled, and we need to build on what their knowledge and their skills. So that's very important to be able to work with them. So there are many, many challenges and research agenda. I will not go through them because I don't have time. But I think that with this book, we have an agenda now on what are the new lines of research. And I think they are really exciting because it's not like, iterating over well-known problems like we do a lot in visualizations, but it's really a new landscape that we need to explore and create a new set of solutions for expanding the world of visualization and data exploration at scale with progressive data analysis. So I think this is really exciting, and we need to break the boundaries between academic domains to do it, but we will be able to address problems that have never been addressable before using our tools. So I really invite you to look at the book, get inspired from the book, and choose some particular questions in order to solve the overall problem and get to the next stage of after replication of empiricism and theories in order to make progressive data analysis real and professionally usable. Thanks. If you have questions, I'd be happy to take them.
All right, so thank you for the presentation. And I got a question. So do you have any inputs on how to deal with users, stakeholders' expectations when we progressively show them data visualization?
Can you say it again? Do you deal with users?
Do you have any inputs on how to deal with users, stakeholders' expectations when we progressively show them data visualization?
Yeah, we had a lot. I mean, we have maybe not a lot, but we have there's been many studies on how users react to progressive output, and all of the studies are clear. The humans can deal very well with progressive processes. I think it's something ingrained in our brain. We deal with progressive processes all the time. So we had studies about comparison with instantaneous, progressive, and delayed answers, and that shows that there is no statistical difference for users from instantaneous and progressive. We were showing a progressive error bars or confidence interval to users, and they were able to deal with it with no problem. We also had experiments with more complex settings. Humans are equipped, so that's great. I think we have to be careful to avoid some issues. but the humans are very well equipped. There is a chapter about the human in the progressive loop in the book that explains all that and all of the issues related to biases that we need to be dealing with. But I think the good news is, yes, the humans can deal with it quite well, and that was great to show it.
Thanks for the answer. And it seems that there are a lot of research agendas in the current slide as you listed.
Yeah.
So could you share your perspective on where we can start? Or can you prioritize the...
Yeah, what would be great, I think, is to be able to share our work. So right now, I collaborated with many researchers, but all the things we've been doing are isolated because we don't have a shareable infrastructure to be running the same algorithm, the same visualization with the same data structure. So having at least one or two toolkits that can deal with the whole pipeline would be great. That's quite technical in a sense, but I think this is very useful to avoid people from creating an algorithm, out there and not being able to apply it for real cases. So it would be great if we could reach a level where we can interoperate some of our work. I think it would help. I'm working on that, but I don't think one solution will be the best and the only one for sure. So I think this one is probably one of the reasons why the domain is not progressing that fast, because everybody is waiting for somebody to create an infrastructure where they could piggyback and create their own small stuff. So I think this is one of the priorities, I would say, for PDA to evolve. And otherwise, we can do work on any of the domains. But as you've seen already, there are already work in SciViz, in machine learning, or databases related to progressive. It's just that it's hard to show something completely full pipeline application that is totally usable from A to Z. So this might be the missing link right now.
All right. Thank you for the answer. And one last quick question. So is there a PDF version of the book already available?
Yes, not already available. We are still finishing it. I mean, really as
okay.
Yes. So it's going to be there by the end of this month or the beginning of next month. It's in proofreading stage. So I think the guy in charge of proofreading sent me an email this morning saying it was done. I need to double check it and then it will be available. So yes, the book will be free, open, and available for download on a PDF format.
All right. Thank you for the answer.
Thanks.
Okay, so it seems there are no more questions, and let's move on to the paper presentations. We have 3 papers, and the first talk is towards a progressive open source framework for SciViz and InfoViz by Sharo Kine.
Hello everyone, and welcome to this talk about unified frameworks for SciViz and InfoViz. My name is Charles. I work at Kitware, where I mainly maintain VTK and ParaView. Today, we will talk about scientific visualization and information visualization, and I will give you a quick presentation in this context of ParaView and VTK, and we will see how we already have interesting features for progressive analysis. However, there are some limitations that still prevent us to completely do it, and we will see what would be the perspective to implement those completely into those softwares. At the end, of course, a small conclusion. First of all, a quick history. When the first time we talked about representing the data in IEEE conference, it was about global visualization. Then we had the information visualization topic coming separately from the scientific visualization topic, and the InfoViz was for abstract data, while the SciViz were for more geometric data. But recently there is a trend where the two are coming once again together into a visualization topic. So there is a convergence in progress. Why so? Currently, information visualization is more for abstract and often high-dimensional data. It will focus on the interaction, the user experience, so we can build specific widgets with specific queries when we build a new application. But there is not a single technology for that. So there is a constellation of tools with frameworks, with languages, with WYSIWYG solutions. In scientific visualization, on the other hand, we are more focused on geometric data, which means that we have 2D and 3D data most of the time, and those can be massives, like the results of large simulations that would be distributed on a supercomputer. On those, we will focus on the exploration parts, and of course, the performance is of great matters here, because we do not want to wait several minutes in between two images, for example. And the base technology for this is only a few frameworks. And recently, there is a trend in InfoVis where we try to get larger and larger data analyzed with the existing tools, but it's not always easy to make them work with distributed computing, so the performance is not easy to achieve. On the other side, for the scientific visualization parts, we have more and more information attached to the result of the simulation with a higher number of scalars, with higher order tensors, and so we have higher dimensional results. And we also would like to be able to help the user explore better the data with more custom interaction, like specifically built queries. And so we can see here that each of the domain has already features that interest the other ones. So I think that would explain a part of this convergence that we have seen. And for this presentation, the goal would be to present how bringing progressive data analysis visualization into SciVis frameworks would be a way to help also people that do InfoVis, because it will help with the interactivity on massive data. But for this, we may need to rethink a lot of things into VDK and ParaView, but not everything. That's what I will try to present you now. VDK is an open source library. It's a BSD3 license. It has been started more than 30 years ago. It's written in C++ and also it's built with CMake. It has a flexible data model, which is mainly thought for geometric data, but not only, and which natively supports distributed computing. We have advanced pipeline abilities, so the pipeline, it's this construction of filters that you make one after the others, and that will give you the processing of your data. And these VDK pipelines, they support lazy evaluation, and they have already some query responders abilities that may be interesting to customize the output of the pipeline depending on the user needs. We have a large choice of rendering methods. I will show you that just quickly after. It's not the main topic of today. And this library is OS agnostic. It works on Windows, it works on Mac, it works on Linux, and we also have some Android builds. ParaView, on the other hand, it's an application. It's also open source, BSD3, and also written in C++. It's based on Qt and of course on VDK. It's available through a binary release, so it's easy for you to download and try it. And you can extend it through plugins written in Python, and if you compile your own ParaView in C++. One of the main features of ParaView is that it has a client-server architecture, which is really convenient when you want to have distributed visualization, for example, in a supercomputer. And ParaView is not just an application, it's a framework, in fact. If you want to build your own application for your specific field, you can take ParaView as a building brick and customize the interface to get a more tuned, a more specific experience, a more tuned user experience. And for both of them, we have a nice community that I still would like to thank today, with a lot of interaction on the GitLab or on the corresponding discourse. Here are some examples of rendering that we can have with VDK and ParaView. So we can see that we have surface rendering with more than one scalar mapping. The same for volume, when we can map two different values into a single volume. But what would be interesting here for the InfoVis people on the room would be the charts view, because as we can see, VDK and ParaView already provides the basics kind of views that we use for non-geometric data. So it's not everything, but it's not nothing. And thanks to the client-server architectures of ParaView, we have different ways to explore the data on the VTK pipeline. We have the Qt interface that we already talked about, and we have here one example with TTK. Julian told you about TTK previously, but we can also explore the VTK pipeline, the distributed VTK pipeline through Pythons, because ParaView comes with a Python's abilities, and so we have a kernel with ParaView abilities directly into IPythons, and we also have a widgets integration on which you can directly interact with the ParaView render view inside a Jupyter notebook. ParaView can also be the target of web queries. We have a web module that we had already for years based on WS Link, but thanks to Tram, which is a new software, it's becoming much easier. Tram, it's a Python's software from which the goal is to glue together the processing bricks and the rendering abilities for building a web application. And you can plug Tram with ParaView, with PyVista, with Altair, with Vega, and with different kind of processing bricks to build your own visualization application. And so if you try to get more closer into the InfoVis parts, VTK and ParaView gets you some real benefits. For example, they support a wide variety of input file, even distributed CSV, for example, if you want to open them. They will already provide tools for user interactions, like you can build your own selection using the mouse, but although using some specific queries with components provided in the GUI. You can extend with Pythons the amount of filters that you have for a specific computation, and it's also true for the view, because we have a specific Python view on which you can delegate the rendering to some Python library. Here on the right we have an example where we use Matplotlib to print some charts coming from a dataset. And as we already told previously, we have some charts view. Here is an example with some mouse selection that has been done in a parallel coordinates, sorry. The data model of VTK is already thought to be able to provide with partial results. This would be close to, this is related to distributed abilities, because to distribute data sets, we need to be able to provide subparts. So each block of each node of the computation will have a subpart of the data. So this would be already a mechanism that we could use to get subpart of the data. But to be completely honest with you, I think the adaptive mesh refinement abilities of VTK are more interesting in this realm, in this regard. And adaptive mesh refinement is a kind of simulation where we locally refine the datasets where where the simulation needs more information. And so we have a hierarchical view on some image data which is available in VTK, and that's already supports some query responder mechanism in order to just update the location of the dataset where it makes sense. And so we reduce the amount of computation. And recently we also introduced the VTK cell grid. It's still experimental, but the whole model here, it's aside from the existing data model, and it's based on a query responder mechanism. So that could be also a good way to get subparts of the data that we want. In terms of executive, the executive is the part of the pipeline that will try to get cleverness around the processing. It already supports things like automatic decimation. We will see that we will try to respect some frame per second. This is also the executive that will handle the message for the query responder's abilities. And that will be in charge of caching some data to have some lazy update where only subpart of the pipeline is updated. But this executive, it's for now, it has like a naive aggregate result filters, and that's something that we will need to improve, as we will see later. For now, we have a VTK for each ability. This VTK for each is a filters that is able to iterate through a specific parameters. It can be the time in the pipeline, it can be the blocks if your dataset has different blocks, and to execute a subpart of the pipeline on these blocks, and at the end to aggregate those results into a new dataset. But for now, the strategy in terms of aggregation are already basics, like just putting things into a multi-block dataset. That will need to be improved to really gather the results into a consistent dataset and to be able to update things little by little. And in terms of interactivity in VTK and ParaView, so we have some dynamic updates abilities where we try to ensure we keep a consistent a minimum FPS, and for that we have a dynamic decimation which is applied on the input. This is especially true during the interaction with the mouse, for example, and then when we release the pipeline will update on the full resolution. And we also have some live stream mechanism on which the pipeline is updated again and again with a listen loop at the end of the pipeline that trigger new updates when something changes in the input. The VTK pipeline is already interruptible. We can stop the execution almost at any time, and the pipeline will stop the computation. Unfortunately, the Qt interface is not already able to exploit this feature because of a blocking call in the Qt interface. It's not a problem. And the query responder mechanism is already supported by ParaView. We talked about it during the AMR part, but it's also in the VTK cell grid part, for example. And of course, we have some user queries and selection. But what would be the limitation and how to overcome them to really get progressive data analysis and visualization? I would say that in terms of data model, we have two main limitations for InfoVis and for PDAV. What would be, we are focused on low dimension and contiguous memory. That is due to the size part of the data, and it will be hard to overcome. And we are mostly focused on flat representation. And for this second point, improving the AMR data model to be able to support more explicit meshes, not only images, but also unstructured meshes with a real hierarchical view, would be a way to help the executive to take the right decision for progressive data analysis. And if we talk about the executive part, here we have the main limitation of the current implementation. It's that we have a huge synchronization in between filters, which means that for now the pipeline executes by taking a whole input, executing one filter, then the second, then the third one, and so forth and so forth. And so for real progressive data analysis, we would need to have an executive able to take advantage of the hierarchical view that we talked about previously to define sub-pipelines that could be applied on sub-parts of the data, eventually in parallel, and then to aggregate those results as they come, so we would have different part of the pipeline updating little by little. So that would be a better way to have progressive data analysis in VTK. As we are in the usual data model, pipeline and rendering parts, we also have to say here that the rendering in VTK for now and in ParaView consequently is not yet distributed for charts. What I mean is that if we try to render a VTK table using any of the plots that we told previously, the data will first come into the rank 0 before the rendering. Quickly before the end, in terms of architecture, there is no high-level grammar in SciVis. It's not a limitation of VTK and ParaView. It's, to the best of my knowledge, it's something that does not exist in SciVis. But thanks to Tram, we have already an integration of Vega and Altair, and so we can start to mix things coming from the SciVis and the InfoVis worlds all together. And last but not least, the modularity. For now, we focus on the HPC systems, which means that we have everything implemented with MPI, and if one node fails the computation because of a hardware failure or anything else, the whole computation will be dropped. But we are working on a ParaView async mechanism on which we have sub-process for the processing, for the rendering, and for the clients. That would be more robust, and that would also help you guys having a way to interact with the data as the processing is coming. And so yes, it's a real asynchronous processing. We are also working on a more Pythonic VTK. That's a way to get more into the Jupyter notebook and other kind of usage of VTK and ParaView. So just to quickly finish, VTK and ParaView already have some nice distributed processing abilities. They already have some support for non-geometric data, even though only a few filters are available here, and we would like to improve this. They allow you to build some interactive tools and application on your own, so please feel free to try them, and you will benefit here from a great community which is always here to help you. And in the things which are incoming soon, we would like to improve the query responder abilities. for example, with the VTK cell grid, and to improve the asynchronous part, for example, with the ParaView async. And here, feel free to try to help us. Here again, the discourse would be a nice way to communicate. Thank you for your attention. Do you have any questions? Hello, everyone.
Okay, thank you for the talk. So we are waiting for some questions. So let me ask a question first. So I agree that both InfoVis and SciVis communities can benefit from what the other has built. And regarding the systems you introduced, many computations and visualizations are optimized to SciVis data sets by leveraging the geometry and topology they have. I wonder if those techniques can be also applied to InfoVis data sets, where there is sometimes no topology or geometry.
So you are right. That's a lot of filters which are already available in VTK, for example, would not directly apply into data with no topology, with no cell connectivity. However, we already have high-level statistics, temporal data, and some filters that are locally applied to each information in the data that would still make sense. This is both a good and a bad news. This is a bad news because it means that a lot of filters will need to be created to work with the InfoVis system, but this is a good news because this means that while implementing these filters, we may ensure all the steps for the progressive data analysis that Jean Daniel talked about previously, where updating an existing filters may not always be so easy.
So, all right. So any other questions? Okay, because we are a little bit behind the schedule, so let's move on to the next talk. And if you have any question on the talk, please post the questions on the Discord channel. All right, and the second talk is Progressive Glimmer, Expanding Dimensionality in Multi-Dimensional Scaling by Marina Evers.
Hello and welcome to our talk on Progressive Glimmer, Expanding Dimensionality in Multidimensional Scaling. There are many different methods for visualizing high-dimensional data. Dimensionality reduction techniques are commonly used to reduce the dimensionality to 2D, which allows us to show the data, for example, in a scatter plot. Multidimensional scaling, or MDS, is a technique to optimize the pairwise distances such that the distances in the 2D embedding represent the higher dimensional distances as well as possible. However, computing an MDS embedding for many high-dimensional data points is computationally expensive. That's where progressive visualization comes in. It allows us to observe the intermediate results of the analysis process. In the following, we will discuss how we can compute MDS progressively. An important question for creating progressive visualizations is how to chunk the data used for the intermediate steps. The existing literature on progressive dimensionality reduction usually adds new data points for each step. So one starts with a subset of points, and new points are added until the entire dataset is present. However, access to the data strongly depends on the underlying data structure and how the data is stored. Adding new data points is not the most effective way if the data is stored dimension by dimension. Therefore, we propose a different way of chunking the data. In each step, we add new dimensions. Thus, all data points are present from the beginning. When progressively adding new dimensions, the points change their positions. This process continues until all dimensions are added and the final result is obtained. In our work, we build upon Glimmer, which is an MDS approximation algorithm that allows for efficient computation of MDS for datasets with many data points. It consists of several steps. I will discuss our modifications for 3 of them in more detail in the following. This includes the optimization of the forces, the termination for each iteration, and the overall multi-level optimization structure used by Glimmer. Let's first look at the force-based relaxation. Here, Glimmer uses an approximation algorithm initially proposed in 1996. Usual force-based relaxation algorithms require considering the forces between all data points, which quickly becomes computationally expensive. That's why Glimmer uses an approximation that consists of a set of random neighbors and a set of nearest neighbors. The nearest neighbors are the closest points that have so far been investigated. The random neighbors are updated randomly in every iteration. In our progressive algorithm, we keep using the same approximation algorithm. However, as we assume relatively small changes in the distances when adding new dimensions, we reuse the nearest neighbors of the previous optimization as an initial starting point when adding new dimensions. As the approximation algorithm considers different neighbors in every iteration, the approximated stress obtained by looking only at currently considered neighbors varies, leading to a noisy stress curve. Glimmer considers this in their termination criterion by using a filter that smooths the stress curve over a certain number of iterations. It bases the termination of the reduction of stress over the smoothed iterations. In the original algorithm, this filter has a length of 50 iterations. Thus, at least 50 iterations of the algorithm are required until it terminates. In our progressive algorithm, we propose two changes to the termination criteria. At first, we noticed that fewer iterations are needed. This can be explained by good initial conditions, which are caused by relatively small changes in the distances when adding new dimensions. Second, we propose a stronger limit on the maximum number of iterations, which can be used to control the latency and create new intermediate representations. The last step of the algorithm that I want to discuss is the multi-level optimization used by Glimmer. Instead of optimizing all data points at once, Glimmer uses a subset of the data points and creates an MDS embedding for these points. On the next level, additional points are embedded based on the previously embedded points. Then, the positions of all points are optimized together using the algorithms discussed previously. This process is continued until all points are embedded. For the progressive algorithm, we can fully focus on the last step and omit the hierarchical structure. Assuming small changes in the distance matrix when adding new dimensions leads to good initial conditions for the final optimization. Therefore, we replace the hierarchical structure of the algorithm by using the result from the previous step, which was created using fewer dimensions of the data. Before looking into some evaluation results, let's look at an example. Here, we use the iris dataset. As the first step, use only the first two dimensions, which do not need an embedding but can be shown directly. For the following step, we can use them as an initial condition and run the progressive Glimmer algorithm to get an embedding for 3 dimensions of the data. Finally, we repeat the process for 4 dimensions and we can see that the stress that was computed concerning the entire dataset decreases as expected. Note that we also obtain consistent embeddings, which makes following the progressive updates easier. Let's look at the quality of the embedding. Here, we notice that it strongly depends on the initialization. In this example, we used an initial embedding created by the original Glimmer algorithm, which resulted in relatively high stress. For the next step, where we add additional dimensions, we see that the result of the progressive algorithm is relatively bad compared to the result when running the original Glimmer from scratch for the considered dimensions. This is also reflected in the Shepherd diagram. However, we notice that the stress for the following steps consistently decreases and the Shepherd diagram also improves. After a few steps, we obtain results of comparable quality or even lower than the Glimmer algorithm for the same dimensions despite the poor initial condition. We can also observe that the stress stays small, more consistently, and often even outperforms the result obtained by running the non-progressive Glimmer. However, note that our algorithm frequently performs more optimization iterations in total over the different steps, which might explain the better result at least partially. When adding new chunks of data for progressive visualization, the order in which the data is added might influence the result. Therefore, let's look at how the order of adding chunks influences the MDS embedding. For this algorithm, we use a spatial temporal dataset representing temperature over time. Each spatial condition corresponds to one data point, and each time step corresponds to one dimension. As this kind of data is often stored by time step, progressing along adding new dimensions is easier than adding new data points. Here we see the results for two different chunking orders. In the first row, new data dimensions are added in the inherent temporal order of the data. In the second row, the data dimensions are added in random order. For the first two dimensions, we see that the embedding looks structurally different. However, the stress is on a similar level. For the following steps, the structure gets more and more similar, while the stress decreases at a very similar rate. This can also be seen here, where the two curves overlay almost perfectly, which indicates that the order of adding chunks of data has little influence on the embedding quality. With that, I want to conclude my talk. I presented a progressive multidimensional scaling algorithm that is based on Glimmer. In this work, we use the CPU version, so future work includes speeding up the computation by using the GPU as in the original Glimmer paper, optimizing hyperparameters, and exploring different applications such as temporally coherent visualizations or also streaming data. With that, I want to thank you for your attention, and I'm happy to answer your questions.
Okay, thank you for the talk. So there is a question on Slido. Would it generally be a good idea to use 2 dimensions of the data as initialization for any dimensional deduction method?
Yeah, that's a very good question. We found that it depends a bit on the data. If you have a data point that you can, a data set, which for a few dimensions you can easily project, you can also start with a larger set. But when we experimented with the spatial temporal data, we also sometimes started just with 2 dimensions as an initial condition and progressed over time. But what we also did was working on an ensemble where we projected an entire ensemble member and then added in each chunk of data another ensemble member. So I would say it depends a bit on what you want to do and what kind of data you have.
Okay. And the algorithm was very interesting to me as it expands to more dimensions, not more instances. So I wonder if we can take both approaches together. For example, we can have a hybrid approach. So the algorithm determines to which direction it expands, depending on some kind of quality measure. So do you see any opportunity in this kind of hybrid approach? Or have you, by any chance, tried this approach before?
We haven't tried it yet, but I think it's definitely there. And also, as we build on the Glimmer algorithm, where there's the iterative refinement of all points together, in addition to us adding new points and adding new data progressively, there's already the second dimension kind of included. And I would say as this adding new data points is basically included in this hierarchical structure, which we then excluded, it's definitely possible, yes, but we haven't tried and experimented with that yet.
All right, we have one more question. So I'm not sure I understand it. Do you need to load the whole data set upfront, or can you download it progressively?
So the way it's technically implemented right now, it's kind of loaded together, but that's a pure implementation issue. So from the algorithm, it's definitely possible to load it progressively. That was the original idea.
All right. Okay, thank you for the answers and the questions. And let's move on to the last presentation. So the last talk is Practical Challenges of Progressive Data Science in Healthcare by Fateme Rajabiasti.
Okay, Thanks everyone for joining the session, and thanks for all the talks that's happening so far. I'm Fatima Vatanura-Javiazi, and thanks for saying my name correctly. I'm from Khartoum University, and this is the work today I'm going to present on behalf of two of my students who have worked on this project. It's going to be about 3 projects that I'm going to talk about. So for the first, maybe I just give a little bit of a context of what we are doing in the lab. So this is the lab I started, Health-Based Futures, when I started my position as an assistant prof at Khartoum. And we do a lot of projects with hospitals and healthcare services and Ministry of Health to create data visualization at large scales for them so that they can monitor and enhance the quality of care in the healthcare setting. So today I'm going to talk about 3 major projects that we did in the lab, creating database for healthcare, but taking a progressive data science lens and pointing to the challenges we faced. Most of the challenges I'm going to talk about is about stakeholder and users perspective, and kind of echoing on what John Daniel mentioned about working with other disciplines and how that was challenging for us working with database experts, healthcare, and us as a visualization expert at the same time. So the first project we worked on was about surgical outcome. A lot of hospitals track and monitor various operational indicators, and the goal is to help patients' health outcome and increase the quality of care. Often they want to minimize resource utilization and cost. So as a whole, let's say to improve overall performance. And these indicators are essential for monitoring and evaluating a hospital as a whole and processes that happens in the hospital. So they wanted to look at bottlenecks where they can have guided evidence-based decision to enhance the quality of care in the hospital. So they approached us and we joined Ministry of Health in our province to make data visualization so they can monitor quality of surgical care. And they wanted to be active and happening in real time and kind of like reading from their database at the same time. So we started designing and developing an interactive database to display these surgical outcomes. And we had a lot of KPIs. We had data from pre-surgery outcomes, pre-surgery measurements during the surgery, and what happened after surgeries. Overall, we had 50 hospitals that were under this province umbrella, and each of them had 15 to 20 indicators, and these were big hospitals with high traffic of surgeries happening. And as you may be aware, in Canada, most of our healthcare is public, so most of the, let's say, surgical operations were happening under this umbrella of 50 hospitals. So one challenge that actually we faced was that when we started working, we had 2 hospitals working with us, and they gave us a sample data set out of all these 50, and they were perfect data. So we had no or little missing data, and that kind of caused a little bit of challenges of how we could, and we had to change some of the design and development once we got data from more hospitals. So that's one of the questions I had, and I wanted to explore this more. How can we support progressively adding data inputs when we have data inputs or data sources added to our database? Another point that they wanted to look at was that to look at the indicators in comparison to other indicator for each hospital. So this scatter plot will be created for them. I'm not showing the exact replica just because of the issues with privacy for the hospital. But basically, we had on the x-axis number of patients with, let's say, one indicator, readmission, and then on the y-axis, we had another indicator chosen by the user, number of patients with infection, let's say, after surgery. And then your own hospital would be a dot in the red dot, and then you will see different other hospitals around you. So we wanted to use progressively to show it to them that, while they're loading this data, they could see other kind of part of the data. And just because one of the issues was with the indicators coming at the same time, there was a lot of delay. So we were just showing partially, and then it was just loading it. It was a little bit challenging to communicate that with the stakeholders because they were feeling like the first few seconds of the diagram that we show it to them, that's what that is, and where are the rest of the data. Another project we had was about, this is patient-facing, so patient-generated data. We have a lot of, these days, a lot of patients collect data, even healthy people collect data about themselves, steps, and their heart rate, and all sorts of things. And sometimes they bring it to a clinic office for the physicians to look at them, to view, and then give them tailored advice. So the goal here was that we again joined with the province healthcare services to see how we can design data visualization that can present and review for physicians this patient-generated data in short clinical times. And this idea was more prominent for patients who had chronic diseases. So these were collecting data for years, and some of the data were continuously collected. And that was a little bit challenging when they brought it to the clinic office. So some of the data were fine. We looked at the patient's data and see what they collect. Some people collected blood pressure, and some just had like stress of the day. And these were often fine and not very difficult to deal with, and could just pop and just be shown in a short clinical visit. One of the challenging parts was the continuous glucose monitor. These are devices that people with diabetes use, and it just continuously measures the glucose, and you get a sense of what's your glucose level at any moment, basically. So this data was becoming super large when it was collected for months, and often happens that patients don't see their physician for 3 or sometimes even 6 months. And once it wanted to be loaded, that was another challenging part that we wanted to look at. So for example, I can show you one of the graphs we made for them. So that was one of them. This is the chart, kind of like an unusual chart. It's just 24 hours of glucose, so it's not 12 hours, but it's kind of like a clock. And it places the glucose for every moment that was measured by the machine in this area. And the areas, the circles you see are basically the numbers. And if they're red, that means they're too high, and yellow is kind of okay. And then blue is kind of okay as well. And then also there are other reds that are too low as well, glucose. So these data, you can imagine this is not many data points right now here. As you can imagine, though, when it happens that there are months of data and it's basically in every moment that needed to be measured, how it can be populated. When we talked to some of the healthcare providers, they mentioned that they really don't need to have that much of the data to be able to make any decision about the patient. And they could just look at it like a glimpse of the data and see if the patient is doing generally okay or having issues. So that was one of the ideas, to just show them a partial data while the data is loading and it's getting processed to be placed in the correct position. And just if the physician is not really interested to look further, just cut the processing, and that was kind of saving them time. The last project I'm going to talk about is smart beds. We had these beds in the hospital that had sensors that could track where the bed is currently, and then if the bed had to have an emergency stop. So the hospital wanted to look at the solutions to visualize and analyze these smart bed sensor transfers, and to monitor the transfers, and to see if there were many stops that had to be done by the nurse that was caring the patient on the bed. So we had live data that was monitoring this, was monitored usually by the head nurse or clinical managers. And this was a high traffic hospital with a lot of bed transfers. So this project is kind of ongoing still, so not much progress to show, but I can show you one of the visualization we made for them to display partial calculation of the KPIs they wanted in this like dial chart. And while they were looking at it, while the data was getting finalized, they could still make some decisions fast because obviously in the emergency cases, their time is pressured until the data get finalized. Just quickly, some takeaway messages from these 3 projects I had in regards to progressive data in health care data science. So we were aware that showing partial data, especially in the healthcare, could be a little bit risky and might be interpreted wrongfully. So interested to know how we can clearly communicate that to stakeholders. We thought we did that best we could. Still, we faced some challenges that people were not 100% sure if this is the full data. And sometimes it was beneficial when we had this time saved basically by progressively showing it to them when the clinician needed to stop the progress just because they knew what's going on with the patient and didn't really need to deal with it or look at the full data to make an understanding. Thanks a lot for listening and happy to take any questions.
Okay, thank you for the talk. So thank you for the interesting talk. Let me ask a question first. I wonder what the most challenging bottleneck is in designing progressive systems for the healthcare domain based on the 3 projects you have participated in.
Yeah, I think for me, maybe also I asked the question as well. It's kind of like dealing with the stakeholders and kind of making sure that they have this understanding. I'm not sure what's the best way to deal with that. Like, let's say if this is kind of left in the hospital and a nurse is using it, how this can be communicated properly. So we could communicate it with people who we're closely working with to make sure they have this understanding. But I'm still puzzled how this could be the best way of communicating this message to kind of end user, if I want to call them. So yeah, that's kind of, let's say, the best takeaway to deal with these communication with the end user that I can say.
Okay, thank you for the answer. I think there is no more question. So that's it. I think that's it for the paper sessions, and it's time to close. So, Jean Daniel, so can you share the slides?
We can't hear you yet.
Okay, that should work now.
Yeah, now it works.
Thanks. So that's the closing, and it was really a pleasure to see you all. I mean, I was personally super happy to and interested to hear all of you talking. So a special thanks to the keynote speaker who made really enlightening talks about what they are working on in terms of research and the future of what we can do with the progressive systems and summarizing many of the issues related to PDA. So thanks to the keynote speakers. Thanks to the paper authors. This also showed a wide variety of questions and ways to answer them from the industrial perspective, but scalability perspective and real software perspective and requests from real users to algorithms that are still evolving. And I liked a lot the idea of having a less simple way of optimizing the projection MDS. So not step by step, but with more sophisticated ways of doing it. That was super interesting. And then applying progressive data analysis and visualization to medical data. This is also what I'm doing a lot, and I think this is super important. And having a wide variety of examples is great to showcase the problem. So I also want to thank the book authors. They have been working during COVID time, and they have been working a lot after COVID time. So this is really an important issue. And now I guess the message is to say now, for all of you who are watching it, you have to tell the word and start or continue working in this domain, because I think we all believe here that this is a real important area, and it will need a lot of research and application work in order to become usable by everyone. So thanks a lot for all that. And thanks a lot for the volunteers working for this who made it possible. I mean, they have been doing such a great work, reorganizing twice, once after Helene, the second time after Milton, and providing us this virtual experience that is really amazing. So thanks a lot for them. Thanks for the students, volunteers, and everybody. So now I'm looking forward to have you download the book when it's ready soon. I can tell you I'm working on it now, and have more for next year. If you have ideas on what you would like to have for the forthcoming conferences, let us know, or the organizers, you know how to reach us. We would be thrilled to know how you would like this kind of workshop or something else to be organized. I think we need to continue. We need to iterate a bit on what's the best way to do it. So again, thanks for your attention, and I hope we'll be able to discuss more about this progressive data analysis face-to-face or virtually somewhere in the world soon. Thank you. Maybe you have a few questions before we completely close the channel, because we have a few seconds left, but not much. Any other question on Slido, maybe? Or
No.
no?
I think if there is more, there's still the Discord channel available.
Yeah.
But yeah, we would really like to get some feedback. So scan the QR code or click the link in Discord.
That's right. Please fill up the survey so we know what you like, what you would like to have next. That's very important for us and for Viz. Okay, bye. Then.
Bye.